Hello, it's Mr. Colati, and today we're going to be going through our lesson on the binomial distribution. Finally, after so much backstory, after learning everything there is about combinations, Pascal's triangle, and binomial theorem, we're finally ready to learn the binomial distribution. So you're going to have to adjust your thinking caps back to the probability distribution function chapter. Remember, we were learning all these different ways of making predictions for certain situations. So this is a long lesson, so we'll try to divide this into two parts. The first part is sort of the proof. We're going to explain the background of the binomial distribution, and then we'll do a bunch of examples. So first, a pair of dice are rolled 3 times. What is the probability that doubles occur twice? So this is a question you could have solved during the probability chapter. I could make a sample space to look at when doubles occur. So I have my first die and my second die. And okay, I could roll a 1, 2, 3, 4, or 5, 6, or 1, 2, 3, 4, 5, 6. So I'm going to roll my pair of dice, and I want to get doubles. So where are the doubles? Well, that would be 1 and 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. We're going to get into the habit of talking about what success is when we talk about the binomial distribution. So in this case, we want to roll doubles. So that's going to be our success. So the probability of rolling doubles, or the probability of success, is 6 out of the 6 out of 36 options here. Or 1 out of 6. And conversely, the probability of failure, the probability of not rolling doubles, is 5 out of 6. And that makes sense. It's very unlikely that we're going to get doubles. Okay, but I want to know the probability that doubles occur twice when I have 3 rolls. So there's a few different options here. I could roll doubles, and then not roll any doubles the third time. I could roll doubles and then not doubles, then doubles. You know, for this sort of situation, it helps to draw a tree. So I have my first roll. I can have success or failure. Then on my second roll, I can have success or failure. And actually, then I have a third roll, and again, success, failure, success, failure, success, failure, success, failure. So there's my first roll. There's my second. And there's my third. So you can see all the different options. Now we want to find the probability that I get doubles twice, so 2 successes. So this branch, success, 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 would not count because there are 3 successes. Oh, but here's one. Success, success, failure. That is definitely 2 successes. Let me find out the probability of this happening. Oh, well, we know the probability of rolling success is 1 out of 6. The probability of failure is 5 out of 6. Then this is 1 out of 6, 5 out of 6. The probabilities are always the same. So the probability of success, success, failure is going to be, and hopefully you remember this from probability days, 1 over 6 times the probability of success again, 1 over 6. Then the probability of this branch, failure, which is 5 over 6. And that's going to give me 5 over 216. Are there any other possibilities of getting 2 successes? Absolutely. I could have success, failure, success. In that case, the probability of success, failure, success is 1 out of 6 times the failure, 5 out of 6, times 1 over 6. Interesting. It's the same number, 5 over 216. Are there any other options? Oh yeah, there's a third possibility, which is not throwing double first and then getting my 2 successes. And no surprise here, the probability of failure, success, success is 5 out of 6 times 1 out of 6 times 1 out of 6. It's the same thing. So the probability of this, or this happening well, I'd have to add up those three probabilities. So the probability of having 2 successes, 1 failure, is 5 over 216 plus 5 over 216 plus 5 over 216. Or, in other words, because these are all the same, it's 3 times 5 over 216, which gives you 15 over 216, which is pretty small. It's approximately 0.0694. So this is a binomial, this follows a binomial distribution. We're going to learn a shortcut that allows us to jump right down to this number without having to draw a tree in the future. But the big thing to note right now is that this final answer depends on the number of trials I have and the probability of success. Everything follows from there. I mean, I can figure out this number 3. This probability of success comes from, this number comes from the probability of success. So we'll get more into this, but we note that those are the two things that are important. And what you actually could do, this was finding the number of doubles, the probability that I can roll doubles twice in 3 rolls. So that if I wanted to fill in this distribution table, I could roll either 0 doubles, 1 double, 2 double, or 3 doubles. Now the probability of rolling 2 doubles, we just figured out, it's 15 over 216. To figure out the probability of rolling 1 double, well, you could go through and figure that out from your tree. You'd have to add up all the probabilities where I have just 1 success and 2 failures. 75 over 216. The probability of having 0 successes, that would be fail, fail, fail. So that'd be 5 over 6 times 5 over 6 times 5 over 6. That's 125 over 216. And the probability of all success, again, we're not going to show the math here, but that's 1 in 216. So this is how we built the probability distribution table, is the number of doubles. And we're just going to show the math is not shown. Okay, so we can see that we can use this probability distribution tree, probability tree to build the probability distribution table. You can see it's a lot of work. And can you imagine how this could get a lot harder? What if I asked you to roll that pair of dice 8 times? What's the probability that doubles occur twice? Well, you'd have to make this massive, massive tree. And then you'd have all these different possibilities. So let's learn the math of the binomial distribution. This that we just drew here, this probability distribution table, follows the binomial distribution. The binomial distribution is written as x belongs to b, and then the 2 parameters n and p. So this is the random variable x. In this case, that's the number of doubles. And the parameters, remember we learned parameters for the normal distribution? Well, we have parameters for the binomial distribution as well. We have n, which is the number of trials, in this case the number of times I throw the dice. And we have p, which is the probability of success. For something to follow a binomial distribution, to know that it has this distribution, there's 4 things you have to look for. And you'll get better at looking for these, but I recommend to always kind of be thinking of them. The first is a fixed number of trials. Again, in this case, I threw my dice. I only threw my dice 3 times, so it was a fixed number of trials. The second thing are there are only 2 outcomes for each trial. So you have either success or failure, and this is really important. It's a very simplified tree that only has success or failure. And you'll see that the example we just had, we looked at either rolling doubles or not rolling doubles. The probability of success is constant. That is, the probability of rolling doubles in this case doesn't change. The trials are independent, so one trial does not affect the other trial. And if you roll a doubles on your first roll, it doesn't affect your second roll. So we know that they're independent. If those 4 things are satisfied, then you have a binomial distribution. René Lepage. So let's look at that same example. Oh no, a pair of dice are rolled 6 times. What is the probability of rolling doubles twice? Well, as you can imagine, this would be a humongous tree. We can't make sense of such a large probability tree. So let's develop a formula. Remember back here, each branch has the same probability. So the probability of rolling 2 successes and 1 failure, it's always the same. So in this case, it'd be similar. We just want to find the probability of 1 branch. So let's look at this branch, the probability of success followed by 4 failures. So we know the probability of success is 1. And again, we'll look at what we did last time. Success times failure. So I have 1 over 6 for success times 1 over 6 and then times 4 failures. 5 over 6 times 5 over 6 times 5 over 6 times 5 over 6. Ooh, that's a lot of difficult math to do in your head. But actually, let me just simplify a little bit. This is 1 over 6 to the power of 2 and 5 over 6 to the power of 4. So you end up with 5 times 5 times 5 times 5, which is 625 over 6 to the power of 6, which I don't know off the top of my head, 6 to the power of 6, which is 46,656. Again, if you wanted to see that as a number, it's a very small percentage. That's the percentage, or the 1% chance of getting success, followed by failure. But remember, this is just 1 branch. We know there's lots of different options. They all have the same answer, but there's lots of different options. There's so the probability of success followed by 4 failures, which is also going to be the probability of, what if we had the failure first, then success, then fail. What if we had the probability of fail, then 2 successes, then the 2 fails? You can imagine there's a lot of different options here. And you can imagine that would correspond to a really complex probability tree. So is there any way we can know how many different branches there are? In other words, is there a way we can find out how many different combinations there are of 2 successes in a group of 6? How many ways can we choose 2 from a group of 6? Well, we learned this. We just did a whole section on this. This is combinations. In other words, we want to know how many combinations there are. Well, there are 6 choose 2 combinations. It's all coming together. 6 choose 2. Let's see if I can do this in my head. 6 choose 2. I'll use the formula, even though you could just punch this into your calculator. That is... You remember how to do this? This is a factorial. So we have 6 minus 2 is 4 factorial. 4 times 3 times 2 times 1 is the same as this. They cancel out. So I'm left with 6 times 5 over 2. That gives me 30 over 2, which gives me 15 combinations. So in other words, how many different branches are there? Well, I can figure it out using combinations. It's 6 trials, choose 2 successes. Last time, similar situation. I had 3 trials, choose 2 successes. Instead of drawing a tree and doing all this work, I could have just done 3, choose 2, and it would have told me there are 3 branches. So here I know that there are 15 combinations. So if you look at what I did last time, I figured out the probability of 1 branch, and then I multiplied it by that combination, 3. So in this case, I'm going to take my probability of 1 branch and multiply it by 15. So let's just develop this as a formula. The probability of 6 trials, 2 successes is 6 choose 2 times 1 over 6 to the power of 2, that's from up here, times 5 over 6 to the power of 4. So you can see how we're kind of developing the formula here. This is the number of branches, and this is the probability of 1 branch. So if I wrote this out, this would be 15 times 625 over 46,656. So that gives me 15 times 625. I get 9,000. I think I divided it all out a little bit. Anyways, my final answer becomes 3,125 over 15,552, which is equal to approximately 0.201. So what's the probability that you're going to roll 2 doubles if you roll the dice 6 times? Well, it's about 20%, which is better odds. And you can see how we were able to, without drawing a tree, jump down to here. So we figured out the probability of 1 branch and multiplied by the number of branches. And I know what you're thinking. Well, what if I hadn't defined success this way? What if I had, here we know I defined success as the probability of rolling a double. What if I had defined success as not rolling a double, and I defined failure as rolling a double? So in this case, the probability of success would be 5 out of 6. The probability of failure is 1 out of 6. So we want to know what's the probability for 6 trials. You have 4 successes, right? Think about it as the same question, where this would mean, so in this case, the success is not rolling a double, so you're going to have 4 not doubles, 2 doubles. So it's the same question. What's the probability of 6? Okay, so let's use my formula. So it'd be 6 choose 4. Then it would be the probability of success, so 5 out of 6, to the power of 4, because that's 4 successes. And then I take my probability of failure, 1 out of 6, to the power of 2. So this is the same, this is the same. What about 6 choose 4? That 6 choose 4. Oh, it's also 15. So it works either way. It doesn't matter what you define as success. And this has to do with the fact that this is due to the symmetry of Pascal's triangle. I can show you Pascal's triangle from a few weeks ago. There it is. But remember, there's that symmetry. So the probability of this combination and this combination are the same. And so that's why there's kind of this duality to it. We can use it in either direction. Okay, so that gives us our formula, or we've just developed our formula for a random variable x that follows a binomial distribution, that is has those two parameters. The probability that x is equal to some value is n choose r p to the r 1 minus p to the n minus r. This is what's on your formula sheet. Another way of writing this is the probability that x is equal to r is equal to n choose r p to the r q to the n minus r. Where, let's just define all these things. N is equal to the number of trials. R is the number of successes. P is the probability of success. And Q is the probability of failure. So, there you have it. This was a long process to get to this formula. The formula that allows us to figure out the probability of a certain number of successes. This is on your formula sheet. You can see it has a combination in it. In fact, it looks a lot like the binomial theorem, right? You have your constant, you have your a to the power of r and b to the power of n minus r. It's all related. It's all very similar. Don't worry too much about how we got here. It's important to understand this, to follow along. This is the formula. And actually, we're going to find when we start looking at examples, you don't even need to use this formula because you have a GDC. So you can go right to your GDC and just type in the parameters, which are n, the number of trials, p, the probability of success, and ask for any value r, and your calculator will spit out those values. So in an archery competition, Paul hits the bullseye 45% of the time. Not great, Paul. If Paul takes 8 shots, what's the probability that he hits the bullseye 5 times? Well, this is not a normal distribution. Remember, the normal distribution was all about measuring something, but this is about getting the bullseye or not getting the bullseye. FYI, bullseye means the center of a target. Now, is this the binomial distribution? Well, if you remember in our last video, we had 4 things we want to look for to show that we're looking at a binomial distribution. So here they are. Here, let's go through each one. The first one, is there a fixed number of trials? In this case, what is the trial? Well, it's Paul shooting arrows at the target. So yes, there's a fixed number of trials. We know in the question he's taking 8 shots. Okay, the second thing, are there 2 outcomes? Is there success and failure? Yeah, well, he's either going to hit the target or he's going to miss the target. So that would be success or failure. Is there a constant probability? Well, yeah, the probability of hitting the target is 45%, so it's constant. It doesn't change. We're assuming that even if he misses, or if he gets the target, he's gonna have the same probability of getting the target next time. So we're also assuming that they're independent. So these 4 things are true. So we know that we're dealing with the binomial distribution. So now we just have to lay out our formula and plug these values into our formula. But let's do some more setup. Let's first define success. So let's let success be a bullseye. Again, hitting the center of the target. So we know that he hits the center of the target 45% of the time. That's his probability of success. His probability of failure then is 1 minus this value. It's the complement, which is 0.55. Again, we talked about this last video. You could define these opposite and everything will still work out as long as you're consistent. Okay, so in this case, we're looking at x is a random variable. Representing the number of bullseyes. So we know that x is the number of bullseyes. So it's going to follow, because it follows these four things, it follows a binomial distribution, and then we need our two parameters. Remember, from a binomial distribution, where is it? Our parameters are n, the number of trials, and p, the probability of success. So the number of trials here is 8, and the probability of success is 0.45. Those are the only two things that you need to make a binomial distribution happen. You need n, and you need to know p. And writing out this line is usually worth a method mark. So I always recommend to write this out. This is the math language that IB likes to see. So now let's use my formula. Probability that x is equal to r is equal to n, choose r, p to the power of r, q to the power of n minus r. There's my formula. Let's plug in my values. What's the probability that x, remember x is the number of bullseyes, we want to know that he gets 5 bullseyes. So what's the probability that x is equal to 5? Well, that would be, here we go, 8, n is 8, that's the number of trials, choose 5. Probability of success is 0.45 to the power of 5 times 0.55 to the power of 8 minus 5, or the power of 3. So we've used my binomial distribution formula. And really, again, this is the formula that we developed last section, right? This is the number of branches, and this is the probability for one of the branches. I can plug that into my calculator. So I have, let's put that down here, over here, 8, choose 5, times 0.45 to the power of 5, times 0.55 to the power of 3. And there we go. So Paul hits the bullseye. Paul gets 5 bullseyes out of 8, 17% of the time. So not great. More useful, the binomial distribution, and where you'll see the questions a lot about this, are related to inspecting parts or inspecting fruit or inspecting something in a factory. Either it passes inspection or it fails inspection. This would be useful if you're running your factory. You want to know the probability that you're going to have to throw away a bunch of product because it doesn't meet your inspection. So new computer chips made in the factory have a 5% chance of failing. That's pretty good, right? 95% of the chips are good, 5% fail. Inspector selects 30 chips for testing. What's the probability that he gets 3 bad ones? Remember, most of them are good, so if he reaches into a bin of 30 chips, he's probably going to get mostly good ones. How many would be bad? Okay, well, first of all, is this a binomial distribution? Well, let's go through all the different things. So, are there a fixed number of trials? Well, yeah, he's taking 30 chips. There's 30 tests I'm doing, basically. Are there 2 outcomes? Well, yeah, a chip can either fail or it cannot fail. And is the probability constant? Yeah, the probability of success is constant. It's 0.05. And these are independent, right? One bad chip doesn't affect the other chips. So yes, this is a binomial distribution. So let's let success be, in this case, I know it's confusing with the language, but let's say success for this binomial distribution is selecting a bad chip. Again, you could do it the other way around. You'll still get the right answer, but let's define it as success be a failed chip or a bad chip. Don't get caught up in the language here, right? Success and failure. So the probability of getting a bad chip is 0.05. The probability of getting a good chip then is quite high. Okay, so now x is a random variable. Representing the number of failed chips. And we know then that x follows a binomial distribution. We're looking at 30 trials and the probability of success of getting one of those failed chips is 5%. Again, that's probably worth a method mark. So now we want to know the probability that you have 3 bad ones. So that would be the probability that x is equal to r. Let's write this out. N choose r, p to the r, q to the n minus r. Could sub in my numbers then. What's the probability that I get 3 failures? Well, it would be 30 choose 3, 0.05 to the power of 3, 0.95 to the power of 30 minus 3, which is 27. And I get 30 choose 3 times 0.05 to the power of 3 times 0.95 to the power of 27. Whew. And I get 0.127, so about 12%, which makes sense, right? If you're reaching in, you have pretty good quality, the chance of getting 3 failures is quite low. Now, what we're going to show you is that we can actually do this with a calculator. Okay, so now we're going to try solving the same question using the calculator. So we're going to go into a calculator page. There we go. And I'm going to use that button I always press, which is menu. That has all of my functions. This is a statistics idea, and it's a distribution. We're going to go scroll all the way down to binomial PDF. Now, if you look, we have 2 here. We have binomial PDF, binomial CDF. We'll talk about the distinction between the two, but this time we're going to use binomial PDF. So we click that, and then it comes up and asks me for some familiar things. The parameters, the number of trials, in this case it was 30, and the probability of success, which in this case was 0.05. Now the x value is optional, but we know in this question it was asking us for the number of, when we have 3 failed chips. So I want to put in x equals 3. I press OK, and there it spits out my answer, 0.127, or about 12%. This is the same number we got when we calculated the answer using the formula. And it's a good deal easier than the formula, and there's less chance for error. There's no problem using your calculator and going right to this binomial PDF function. You do not have to use the formula we used when we first solved this question. You can almost do this as a shortcut. So there we go, very easy. Now the one thing I will show you, let me just go back to menu, statistics, distributions, binomial PDF again. 30 was n and p was 0.05. If I don't type any x value, watch what happens. I get a whole bunch of answers. Well, this is the entire probability distribution table. So this is when this first number is when x equals 0, when there's the probability of having no bad computer chips. This is x equals 1, x equals 2, x equals 3, and so on. These curly brackets mean that the calculator is outputting the numbers as an array. So it's basically like a table of all of the different values. It's a little impractical because there's so many numbers. That's why I prefer to use the x value and just kind of zero in on the exact number I'm looking for. So again, there's the what we just looked up. We just showed you with the calculator. The binomial distribution can be found using the GDC. You press menu, statistics, distribution, binomial PDF. That was what we just used for this example. So this is the probability distribution function. So this here means the PDF stands for probability distribution function. And the numbers are n and p, which are my 2 parameters. And then of course, what is r? And as I showed you, if you omit r, you will be given an array of all possibilities. So you can see we've got the exact same value, 0.127, when we use the GDC. More interesting to us though is not what's the probability of getting 3 failures, because that's not great. I mean, probability of 3 failures is bad, but 2 failures would be bad too. 1 failure would be bad. So we're usually more interested in what's the probability that there is at least a certain amount. So in this case, what's the probability that there is at least one failure? So that would mean you could have one failure, two failures, three failures, four failures, right? At least one. So in this case, for part B, it would be the probability that x is greater than or equal to 1, right? Just as I said, that's the probability of one failure plus the probability of two failures plus all the way up to the probability that all 30 are failed. Now, a few things here. First of all, you can imagine the giant probability distribution table, right? X can be any value from 0 to 30. So this is, and then we have probabilities for each of them. And this is basically asking you to add up 29 of those probabilities. This would take a long time, right? You'd have to find the apply this formula to each one of these and then add them all up. The other thing to note is that the probability of x is greater than or equal to 1. In this case, the greater than or equal to, there's a distinction here. We want to know at least one failure. So that means we include the probability of 1, greater than or equal to 1, plus 2, plus 3, plus 4. So that unlike in the normal distribution, where the greater than and the greater than or equal to sign don't matter, they're the same. In this case, they're different. So make sure you're careful about counting here. Of course, we know that we don't need to use to do all these probabilities. We have a shortcut that we could use, which is the complement. This is 29 of my possible 30 probabilities. I'm just going to find the complement of the having 0 failed chips. So this is using the complement. Now I can apply my formula, which is 30 choose 0, 0.05 to the power of 0, 0.95 to the power of 30. We know that anything choose 0 is 1, anything to the power of 0 is 1. So this is really 1 minus 0.95 to the power of 30, which is 0.2146. 1 minus that answer gives me approximately 0.785. So you have a 78% chance of having at least one failure, which isn't great, right? Think about this. It was saying your chips are all pretty good, but when you take 30 of them, you have a pretty high chance of having one failure. So if you're sending a box to Future Shop or Best Buy, one customer is going to be pretty upset. There's a pretty high chance you're going to have an upset customer. Again, we can solve this using the GDC. Okay, so we're going to try to do this question with the GDC. So I'm going to, again, go to Menu, Statistics, Distributions, and this time I'm going to scroll down to Binomial CDF. This CDF means a cumulative distribution function. So in this case, it's very similar. I have my n value, number of trials, which is 330, the probability of success, which is 0.05. But now it's going to ask me the lower bound, the upper bound. The CDF, or cumulative distribution function, is going to add up a range of different probabilities. So in this case, we were looking for the all of the x values from 1 up to 30, right? It was quite a few options. So this is going to instruct the calculator to calculate all those values and add them all up. And we find that the probability is 0.785. This is the same thing we got when we did it by hand using the complement. Again, it's totally valid to jump right to the calculator and get this final answer. You don't have to use the complement to solve this question. So like we just showed you, this binomial PDF, which was statistics distribution binomial PDF, is when you're trying to find one R value, which is probably not something you're going to do as often. We're more interested in the cumulative distribution function. So this is menu statistics binomial CDF. This is similar. You put in the n value, you put in the p value, the two parameters, but then you put in a range of r's. So you put in a lower bound and you put in an upper bound. And you saw in that last example, we put the lower bound of 1 and the upper bound of 30, and then we got the same answer, 0.785. Finally, what is the probability that 5 or fewer chips are failures? Again, one of the hardest parts here is thinking of the length, like what is it asking for? 5 or fewer. That means we want 5 failures, or 4 failures, or 3 failures, or 0 failures. So essentially we're looking that x is less than or equal to 5, which would be the probability that x is equal to 0, plus the probability that x is equal to 1, plus ... plus the probability all the way up to x is equal to 5. Remember, 5 is included in this range. Now, I'm not even going to bother to use the formula. It would be a lot of work to go use the formula here, 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 and here. So, and this is totally legal, you're just going to use your GDC. You don't need to do any, you basically don't even need to use the binomial distribution formula because the calculator is so powerful. You put in your parameters, don't waste any time, and you get... Okay, and so for this last question, we go to menu, statistics, we go to distributions, and this is a binomial PDF or binomial CDF? Oh, well, we're adding up a bunch of probabilities, so it's a binomial CDF. I put in my number of trials, which is 30, my probability, which is 0.05. My lower bound goes from 0 all the way to 5, and it's good I wrote that line in my work, so it's very clear what I'm doing. And then when I press OK, it spits out the number 0.996. We round that to 0.997. 0.997. If I was marking this traditionally how it's marked, this setup is worth 1 mark. You get a mark for writing out what you're telling the calculator to do, and then 1 mark for your final answer. So even though this is a long lesson, this is complicated, there's a long backstory, it really boils down to 1 formula or 1 function even on your calculator. So don't draw it out, don't do more work than you have to. This is a perfectly acceptable final result. Okay, let's turn the page. Now, when we're looking at binomial distribution, we might be asked to talk about the mean and the variance, or the standard distribution, or standard deviation, sorry. We might be asked to find the mean or the variance or standard deviation. These have very clear formulas. They're on your formula sheet. They're often forgotten, but the mean, or the expected value, is n times p. So n number of trials times the probability of success, and the variance is npq. These are both on your formula sheet. These are very easy questions that you'll see with this. You literally are just plugging into a formula, but you're going to forget about these formulas, and then you'll forget about how to do these questions. So in a small city, 65% of residents are opposed to a new light rail system. That's not great. I would hope it would be higher, or like nobody. We should all be in favor of new light rail systems. Okay, so if I called up 1,000 people, how many people would be opposed to the new system? Well, is this a binomial distribution? Let's see. Does it have a fixed number of trials? Well, yeah, it does. You're calling up 1,000 people. Are there 2 outcomes? Yeah, they either say, yay, I like this idea, or nay, I don't like this idea. Is there a constant probability of success? Yeah, because we know 65% of people are not going to like this new system, and then we know it's independent, right? One person does not affect the other. At least that's what we're assuming. You know, in theory, people call each other and have echo chambers on the internet. But, okay, so this is a binomial distribution. Let's let success be opposition, the people who are opposed. Again, what kind of people are opposed to a new light rail system? So we have P is equal to 0.65 and Q is 1 minus that, so 0.35. X is a random variable representing the number of opposed people. In other words, x follows the binomial distribution of 1,000 and the other parameters, probability of success, 65%. Phew. So now we just use our formula. It's very easy. If 1,000 people are polled, how many people? So this is not asking me for a probability. This is asking for how many people, or the expected value. This is where people get confused. But it's not asking you for probability. It's asking you for expected value. So the expected value, it's an easy formula. It's n times p, which is 1,000 people times 65%, which is 650 people. I mean, this makes sense, right? If you have 1,000 people and 65% of them are against it, then 650 people should be against it. What about part B, which is asking you for the standard deviation of those results? Well, again, it's an easy formula. Standard deviation is the square root of variance. So it's the square root of this formula, which is np1 minus p. So that's the square root of 1,000 times 0.65 times 0.35. Type that into my calculator. So 1,000 times 0.65 times 0.35, root of my answer, and I get approximately 15.1 people. Two easy formulas, don't forget about them. Look at one very tough example on the back of a Backpage. So, a new drug has 85% probability of curing a patient within 1 week. How many sick patients must take the drug so the probability of at least one uncured patient is greater than 0.95? First of all, this is very confusing what it's asking us. So I have a drug that's pretty successful. And I am interested in how many people need to take this drug so that I have someone who it doesn't work on. So I have someone who the drug doesn't work. For example, if I have one person take the drug, probably they're going to get better. If I have 2 people, probably they're both going to get better. Maybe if I have 100 people, at that point I have one person who is not uncured. This is, especially talking about vaccines and different drug trials right now for the COVID problem, you can imagine that the success of the treatment is really important, right? Sure, if you can make a vaccine, that's great, but if it doesn't work, then you haven't really solved your problem. So let's look. Is this a binomial distribution? Well, first of all, is there a fixed number of trials? Yeah, there's a fixed number of people taking the drug. I just don't know. The problem is that makes this question difficult. I don't know how many people we're talking about. Are there 2 outcomes? Well, yeah, the person is cured from the drug or not cured. Is there a constant probability of success? Yeah, we know that drug has an 85% success rate. And does one person affect the other? Probably not, right? We're going to ignore any placebo effects. So there's a binomial distribution. So yes, it is. So let's define success then in this case. Let's let success be a cured patient within 1 week. So that would be the probability of success we know is 85% from the question. The probability of failure then is, oh shoot, sorry, I did this wrong. Let success be the uncured patient, so someone who didn't get better. So we know that the probability of not being better is 15%. The probability of getting better then is 0.85. Okay, so let's let x be a random variable representing the number of uncured patients. And again, sorry, I forgot that. We're gonna formulate the question, so we're defining success as someone who doesn't get better, which you'll see how this is useful. So X follows a binomial distribution. I don't know how many people, but I want to know, and I know the probability of success is 15%. So this question is asking, again, how many people do I have to test to ensure that I get one patient who doesn't get better? So if you want to think about this question, this is where I find the trick is when you get a really tough problem, I always like to be able to draw something. So in this case, I want you to imagine the probability distribution table. Remember we did that. And remember, that's all we're doing in this section. We're trying to bypass the probability distribution table. So you have X and the probability that X is equal to X. You remember doing these things? Okay, so you could have, so X is the number of uncured patients. So you could have 0 uncured patients. We're not really interested in 0 uncured patients. We want to find 1 uncured patient. So we could have at least 1 uncured patient. So we could have 2 uncured patients. We could have 3 uncured patients. We could have 4. We could have all the way up to however many number of patients I'm going to give this to. So again, I could give it to 1 person. Most likely they're going to be okay and they're going to be cured, so I wouldn't meet what I'm looking for. I could give it to 2 people. Most likely they're both going to be okay. How many people do I need to give it to so that I have at least 1 person who's not okay? So all of these greater than 1, so either 1 who's not okay, 2, 3, all the way up to n, I should add up all these probabilities and set them greater than 0.95, because that's what the question was asking. I want a 95% chance that I have at least 1 uncured patient. Again, this would be good for a drug company to know when they're making a vaccine of some sort. So that's really what this question is asking for. I find this is the way I understand it best. So I want to know the probability that X equals 1 plus the probability that X equals 2 plus all those other probabilities up to the probability that X is equal to n. That's going to be greater than 95%. I can rewrite this. Well, this is all the X's from greater than or equal to 1. Again, it's greater than 95%. We know this then is the complement, right? I can find the complement just by looking at the subtracting this subtracting from 1 the probability of no successes. So 1 minus probability of X is equal to 0. We'll just make a little note of what we're doing. So that was the complement. Okay, now let's plug this into our formula. So I have 1 minus n, which I don't know what it is, choose 0, and then I have 0.15 to the power of 0 and 0.85 to the power of n minus 0. So that's my binomial distribution formula. Okay, well, a few things here. Anything choose 0 is going to be 1, and anything to the power of 0 is going to be 1. So I end up with 1 minus 0.85 to the power of n is greater than 0.95. Okay, well, now this is just a exponential equation I have to solve. First thing I'm going to do is collect my like terms. So this is a number, and this has an exponent. So I'm going to move this to the other side. I'm going to switch these two. So I have 1 minus 0.95, and then this becomes 0.85 to the power of n. I'm just going to say that we collected like terms. This inequality, if you remember solving inequalities a long time ago, I can still treat it like an equal sign. The only problem is if I'm dividing by a negative, then I have to switch its direction. But so far I haven't done that. 1 minus 0.95 is 0.05. Okay, and now I get to this point. and I need to solve an exponential equation. And hopefully you remember how to do this, and I'm waiting for you to say it. Right, we log both sides. So I'm going to log the left side, and I'm going to log the right side. That is our strategy for solving exponential equations like this. Log both sides. Wow, this is getting very exciting. So let's go up here. Now the great thing about logging both sides is that now I can bring this n down using the log laws. So I end up with log 0.05 greater than n log 0.85. Now all you have to do is get n by itself. But this is where you have to be careful. Log of a decimal is always negative. So what I would actually recommend doing is convert these into numbers first before you start messing around with your inequality. Log 0.05 is negative 1.30103, and log 0.5 or log 0.85 is negative 0.07058. So when I divide these, I have to change the direction of my inequality. So we'll just make a little note, only flip inequality if dividing by negative. Okay, and now I can try to use my calculator to do that. So it was negative 1.30103 divided by answer. So I have 18.433 less than n. And now this is that last kind of brutal IB type question with inequality. How many patients then do I need to choose? Well, I need to choose an n that's larger than 18. So I can't have 18.4 people try to test, so I have to have 19 patients. So think about what this was asking. You have some cure that's pretty good at helping people. If you have 20 people have the treatment, there's a 95% chance, or sorry, 19 people take the treatment. You have a 95% chance that one person this isn't going to work on them. And that's important to know how effective the treatment is. And so your homework for this long section on the binomial distribution is, first of all, from the first half of the lesson. So part 1, you do page 531, number 1 to 3, 533, number 1, 3, 4. And then the second part of the lesson, you have page 533, number 2 and 5 to 7, page 535, number 1 to 4, 537, number 1 to 8. And if you want some questions that mimic this last difficult question, that would be page 534, number 1 to 5. Good luck with all that, and we'll see you next time.